Hey guys, Professor Zed here. Thank you so much for watching this video. Meeting number 14, unfortunately I was sick and had to cancel. So there is no meeting number 14. Meeting number 15, the video you're currently watching, is the next video posted for this series. Once again, thank you for watching this video, and I will see you next time. Good evening and welcome back. Another relaxful spring break. Physics. It's the next 2 days. Starting with work. Work is fairly simple. I'm exerting a force to move the chair a certain distance. I perform work. SI unit is the joule. It's a Newton meter. Another common measurement is the foot-pound. There is another unit for work. Calorie. Joule and calorie. They should sound familiar. There's also units for energy. Which means work is energy. It's just energy that you're outputting, the forces exerting. Several ways work can occur. Say that an object is being moved L units. In a straight line. It's important, it's one-dimensional. Under constant force F, work is then force times distance. Of course, it's very rare that the force is constant. Usually, force varies. Now suppose that the force is variable. Specifically, we're considering force as a function of its position. Then work is the integral from a to b of f of x dx. Integrate f along the path. That's as far as what we're going to consider in this course. So technically, force and position are vectors. You'll tackle that in Calc 3. Or intro mechanics. You cover in intro mechanics if it's a constant force, I believe. I don't remember doing path integrals in mechanics. If it's a variable force, then you have to do a line integral, which is the end of Calc 3. I don't remember ever doing that in intro mechanics. One of the common types of problems that we examine when we deal with work has to deal with springs. And springs are governed by Hooke's law. If a spring is being stretched or compressed, say x units, beyond what's called its natural length, right, or its equilibrium position, the spring is going to exert a restoring force. The magnitude of that force is K times X. The direction is the opposite direction. So if the spring's being compressed, the restoring force is opposite, wants to expand it back out to its natural length. If you're stretching the spring, you have a restoring force that's trying to compress it back to its natural length. K is known as the spring constant. So what this means, the magnitude of the restoring force is proportional to the distance it is stretched or compressed. By convention, we take compression to be negative direction. We take stretching to be the positive direction. We would take 0 to be its natural length. And so that would be the position at equilibrium. Oh, that's right. I forgot I don't have it paired with this device anymore. Let's fix that. Perfect. I'm being told spring has a natural length of 10 inches. 800-pound force stretches the spring to 14 inches. We want to find out how much work is done in stretching the spring from 10 to 12. Well, remember what work is. It's the integral of f of x. We need to determine our force. Well, Hooke's law says we're going to have k times x. We have to determine that k. Right? It's a constant of proportionality. We don't know what it is. But they tell us it takes 800 pounds to stretch the spring from its natural length of 10 inches to 14 inches. All right, 14 inches, 4 inches beyond equilibrium. So x would be 4.
F of 4 is going to be 4 times K, which has to equal 800. So that makes K, what, 200?
Yep.
And what are the units?
Inches.
It's the pound inverse inch, or pound per inch. Force is 200x. Work. Going to be integrating, right? Integrating 200x dx from what to what?
From 10 to 14. Or if you go on A from 10 to 12.
Would be 10 to 12. Remember what x is measuring.
Next units.
It's 0 to 2.
It's 0 to 2. Right? 10 represents natural length, so x would be 0 there. Right? X measures how far it's stretched or compressed.
Okay. So if we're doing an example, A will be 0 to 2.
Yes, right? Because natural length is 10, so x is 2 or 0. Goes out to 12 inches, x would be 2. It's stretched 2 inches. Hundred x squared from 0 to 2. $400. What would the units be?
Joules.
This is not SI. Sadly. The inch pound. If you wanted to convert that to foot pounds, what would you have to do?
Divide it by 12.
That's divided by 12 inches.
Yeah.
Right, multiplied by its conversion factor 1 foot per 12 inches. So it'd be 400 over 12, which is what? 100 over 3 foot pounds. Which isn't that much. Then you divide that by roughly 3 to get joules. No. That would give you the meter pound. You then have to multiply by the conversion factor pounds to newtons, which I actually don't know off the top of my head. I think it's going to be a lot smaller though. How far beyond its natural length will 600-pound force stretch the spring?
That's 1600.
Uh-huh. Okay. We know force is 200x, and that's going to equal 1,600 pounds. So what's x?
8.
8 what?
Pound inches or pound inch inverse.
Inches? Just inches.
Yeah, inches.
So it's stretch it 8 inches beyond its natural length. So it'll be a total of 18 inches in length. So it takes a force of 27,714 pounds to compress a coil spring assembly on a New York City Transit Authority subway car from its free height of 8 inches to its fully compressed height of 5 inches. Oh, learn how to spell. That'd be nice. That looks better. We're now told that the assembly is compressed by 1 inch. We want to determine how much work it took to compress the assembly the first ½ inch and then the second ½ inch. And we're told to round to the nearest inch pound. Okay. First thing we need to do is determine the force. All right. Well, we're told it's going to be compressed by 3 inches. So that should technically be -3. Yes. Yes. So that'd be -3x. Not 3x. 3k. And what should that equal?
It's 21,714.
Very close. Why negative?
Because it's a compression, not a stretch.
The force is compressing it. So we're going the negative, or actually compressing this. Yeah, if we're looking at the subway, right, you're pushing down on it. Either way, it's compression, that's the negative direction, so force is negative.
But it's negative 3K equals that, right?
Yes. Again, because it's being compressed by 3. Which means K is
7238.
units of the inverse inch pound, or pound inverse inch, pound per inch, whatever. So again, it is custom. If you notice, even up on the screen, it's hyphenated, right? So that's not on the screen. That's not inch minus pound. That's not pound minus inch inverse. It's a hyphen. They do the same thing with the Newton meter. And if you write Newton meter, there's a hyphen. That's just custom. That makes our force 7238x. Work for the first half inch of compression. And we integrate from what to what?
0 to 3.
It won't be 3.
Or 4.
It will be 4.
2. Is it 1? Oh, is it? Oh, no. Then 0 would have been at the top.
What were you going to say?
Would it be negative 3 or something?
I agree, it's negative,
Okay.
but not 3.
Negative 4 or negative 1? For the first half inch, is it negative half?
Negative 0.5.
Okay.
Remember, for integration, no one said your lower limit had to be smaller.
Oh, okay.
Right? All this means is we're going from 0 to minus 0.5. We're moving in the negative direction. The idea of direction becomes very important when you study line integrals in Calc 3. It'll be 7238 over 2x squared. What? 3619?
Yeah.
Do this and that equals so. X squared. But that's 0, it's just 0. So it becomes negative 0.5 squared. Which is 0.25. So what's 3619 divided by 4? And remember, they only want to the nearest inch pound. 905 inch-pounds. So it takes 905 inch-pounds to compress the spring that first half inch. What about the second half inch? Now where do we integrate from?
Is it negative a half to negative 1?
And 1/2 to negative 1. No. Yeah. Negative 1 squared is 1, right? So it's going to be 3619 minus 3619 times 0.25, which was 905. We already did that, right? You also could just do 3619 times 0.75. 1 minus 0.25. Either way. What does that give you?
2714.
Well, that's interesting. This is saying it's taking about 3 times as much work to compress at that second half inch as the first half inch. Have you tried compressing a spring? Oh dear, this may be more difficult. I don't even know if I have anything that's springy. I don't think there's anything in here I can have you try it. That result lines up with real life. Find a spring assembly and try and compress it. The more you compress it, the harder it gets. Because its resisting force becomes stronger the more you compress it. Same thing with stretching. The farther you stretch it, the harder it's going to become. So that result does actually line up with reality. Okay, that's enough on springs. Springs are boring. Unless you're studying a double spring problem. That becomes very interesting. Has anyone taken intro mechanics? You guys are so boring.
I've taken mechanics of solids and statics.
That's not mechanics, it's engineering. It's in chem.
We did do an experiment though where we compressed nails like bolts.
A classic mechanics problem is called the pendulum problem. In intro mechanics, they make it really easy because there's no resistance. So it's just periodic motion. It's oscillatory and it continues on forever. Then you get to study advanced physics, advanced mechanics. Throw in the friction now and study it. And then they go, oh, that's not good enough. Here's double pendulum. Pendulum on a pendulum. Study that motion. I think there's a double spring problem too. Particle of mass m is at the point x0. It is a I swear I was not drunk when I typed this. Attracted toward the origin with a force whose magnitude is k over x squared. The particle starts from rest at x equals b and is acted on by no other forces. Find the work done on it by the time it reaches the point x equals a, and assume that a is less than b. So our particle's starting there. Right? It's going to end here. And it's an attractive force towards the origin, towards 0, with a magnitude of k over x squared. So in other words, this attractive force is proportional to 1 over x squared. 1 over the square of the distance from the origin, or from the center. This is known as an inverse square force. Technically, it's an inverse square field. Now that's advanced. Inverse square forces are very common in physics. There are 2 of them that you experience every single day. It's actually 3. The first is the most obvious. Gravity. Gravity is an inverse square field. There are 2 others that go hand in hand. Electric force and magnetic force are both inverse squares. Right. Also happens to be radial. But again, you'll discuss that when you study vector fields in Calc 3. Keep in mind that even if I'm out here, I'm still being pulled towards the center. With a magnitude proportional to 1 over x squared. We're actually going to look at gravity. The force due to gravity, and we'll find what its constant is that's been calculated. Of course, what that means, the further you get away from from the center, the weaker the force becomes. Right? Because you square the distance and then take its reciprocal. We are not told what K is in this case. So work. Integral from what to what?
B to A.
From B to A. And what is the integrand?
K over X squared.
What is that antiderivative?
Is it K times 1 over X?
Close.
Because K is a constant. Negative K over X. Oh, because it's a negative one coming out. Yeah.
That gets evaluated from B to A, right? So we're going to get negative K over A plus K over B we can flip the order. K over B minus K over A. Or right as a single fraction doesn't matter. This result's interesting. They tell us that what? A is smaller than B, right? Is this positive or negative then?
It's gonna. I mean, and that, and with this problem, it would be positive because it's assumed.
Is it? A smaller than B. A minus B.
A is smaller than B, but they would both be bigger than 0.
True. So they're both positive.
Right.
So you take a smaller number, subtract from it a larger number. What's the result?
Oh, that would be negative.
This is negative work.
Yeah.
That means that you're gaining energy. So this particle is gaining energy from this system as it moves. It's interesting. It's not exerting energy. Right, so if I were to move this, it would essentially cost me no energy. Why? Because it's already being attracted to the origin. I don't have to do anything. Right, so you only have to exert work if you're opposing the force. I have to exert energy on this. What force am I having to overcome?
Like moving and you're trying to move it.
Right, so what force is resisting me?
Is that like a sort of friction?
Specifically rolling friction.
Yeah.
Well, actually, there's two types of friction. First, I have to completely overcome static friction to start moving. Then once it's moving, it becomes rolling friction.
Static friction is the amount of friction you have to overcome in order to even move it at
Yes.
all. Yeah.
You worked in a warehouse? Probably, maybe not, but if you've been grocery shopping, you see pallet jacks and
Yeah.
pallets. Yeah, what's the purpose of the pallet jack?
Make it easier to move things around.
Right, because what does it do? It converts a
Static friction.
flat object, which has a lot more friction. So what is that? That is, it's not called static. It's a kinetic friction, might be, whatever. Into rolling. So if you try to push a pallet, and I use this because I actually work in a warehouse, we would get literally 1 ton banana pallets in. The pallets weighed 1 ton. Yeah, try and push that. It ain't happening. That bastard ain't moving.
Not even have the things built.
Lift it up on a pallet jack though. Now it moves relatively easy. Just don't walk in front of it because it's going to take a while to stop. Yeah, I had some idiot think that would be a good idea. It did not end well for them. Thankfully, I had witnesses to say they walked in front of me and gave me no stopping distance, so I didn't get in trouble. This one's fun. We're going to use Newton's second law of motion to show that net work done by a force in moving an object of mass m along the x-axis from x1 to x2 is given by the change in kinetic energy. So that's another way of calculating work. You can also just determine what is the object's change in kinetic energy. That's the work that's done. What is kinetic energy?
Like the amount of energy it has while it's moving.
Be careful. Because it's not amount of energy. That's something totally different. That's total energy. Kinetic energy is just the energy of motion. Because you actually have energy right now. It's called potential energy. Potential energy is measured height from the center of Earth. The higher you are, the more potential energy you have. Then you also have thermal energy. which is heat.
So kinetic energy is just.
It's just one form of energy. There's several forms of energy. One of the most important laws in physics which I sadly cannot prove in this class, but I do prove it in Calc 3. Something you have heard of. It's probably the most important law in all of physics. Conservation of energy. That is misunderstood. You're driving. Let's say you're being very daring. Driving 120 miles an hour. You slam on your brakes. You come to a complete stop. What happens to that kinetic energy?
It becomes some other type of energy?
What type, specifically? Guess you've never worked on cars either.
Well, your brakes have to make you stop, right?
Right.
So the brake pad is rubbing against
What kind of energy does it become?
friction. No?
There's no friction energy.
No, because it's just like burning through the brake pad, right?
Burn. What's associated with burn?
Thermal.
Heat becomes thermal energy. You ever tried to change a brake after driving it? Ha ha! Have fun. You're going to get burned. So the kinetic energy became heat energy. Two ways, by the way.
Yeah.
Into the brake pads, but also
The tire.
rolling friction. Right, so you heated up the road. Is energy being conserved? Because what happens if you sit for a while? What happens to your brakes?
Cool down.
They cool down. But you're not gaining energy back, are you? No, that heat radiates away. Uh-oh, what happened? Change in energy is supposed to be zero. That's what conservation of energy says.
It became a different kind of energy.
No, it's gone.
So
This is where it's misunderstood. Because conservation of energy says change in energy in a closed system is zero. Your car is not a closed system. So there was no violation. The only closed system I know of is the entire universe. So yeah, conservation of energy. Same thing with conservation of information. That's also only for closed systems. A lot of the conservation laws are only for closed systems. Misunderstood. Kinetic energy. One half mass times square of the velocity. What is Newton's second law of motion?
force? No,
That's the first law.
that's the first law. Second is inertia.
Newton didn't say anything about inertia.
No.
Well, maybe he did, but it's not his laws of motion.
Mm-hmm.
Right, so there's three of them. First one, object at rest stays at rest, object in motion will stay in motion unless exerted on by an outside force. Third law, every force has an equal and opposite force. That law hit me back. In fact, it's the third law that allows you to walk. Right? What's propelling you forward? The ground pushing back on you. Second law is his most famous. Force is mass times acceleration. That's his second law of motion. He was wrong. Force is not mass times acceleration. Force is change in momentum. So momentum is defined as mv, mass times velocity. So what happens if you differentiate this with respect to time? Well, you would think, oh, well, it's just mass times change in velocity, which is acceleration. You made one critical flaw. You assumed the mass was constant. Mass is not constant. Mass is a function of speed. The faster an object moves, the more mass it has. That is known as general relativity. No, special relativity. Time is also not constant, by the way. Time is a function of speed. The closer you move to the speed of light, the slower time moves forward. Luckily for us, I think we can assume that we're moving at speed so slow that change in mass is negligible. Which is why intro mechanics and Newtonian mechanics uses Newton's second law, because the speeds are so slow, you can just ignore the change in mass. You can treat mass as constant for sublight speeds. Once you start to get really close to the speed of light, you can no longer use Newton's second law. You have to use change in momentum. Because now mass isn't constant, you have to account for that. I'm sure you've seen that too. And that's also relativity. E equals mc squared. Well, c is a constant. That's a universal constant. It's the speed of light. This is a very powerful statement. Mass Effect 2, I think it was. There's actually a little bit of dialogue in there on the Citadel, if you listen to it, about propelling slug. I think it was using Newton. punchline was Newton's the deadliest son of a bitch ever. No, Einstein is the deadliest son of a bitch ever. How do you think the atomic bomb works? E equals mc squared. How do you think the sun works? E equals mc squared. Two hydrogen atoms fused together to form helium. Believe it or not, a helium atom is slightly less massive than two hydrogen atoms. Yes. So to balance it, you have to exert energy, lost energy, which is propelled. That's how the sun radiates. That is called nuclear fusion. The atomic bomb is nuclear fission, I believe. This is what we're using. Work. The integral. Particles moving from x1 to x2. Integrandus force. Since we're treating mass as constant, right, we're assuming sublight speeds, we can factor it out. But A, acceleration. dv dt, right? Oh dear. That is a problem. Velocity is a function of time. We're integrating with respect to x. But that's okay. Because we can use chain rule. To write dv dt as dv dx times dx dt. Right, and the reason this works, yes, velocity is a function of time, right? But so is your position. Your position is also a function of time. Which means inherently, velocity can also be run as a function of position. Right? Because your position changes with respect to time, which causes your velocity to change. Well, if velocity changes as you move, that makes it a function of position. So the same can be said, the same is true about mass. Mass is technically a function of speed, but speed is a function of time, which means mass is also a function of time. This now becomes dx dt is velocity, right? This is now U substitution. Function times its derivative with respect to x. So you let u be v is, or du is dv dx. Times dx. So what is the antiderivative? It's just 1/2 v squared, isn't it? But remember, our velocity is a function of position. So it's 1/2 mv of x2 squared minus 1/2 v of x1 squared. Final velocity squared, initial velocity squared. But wait, kinetic energy is 1/2 mv squared. So this first term is your final kinetic energy, minus that second term is your initial kinetic energy. Well, if we do final minus initial, that is the definition of change. And there you go. Work is just changing kinetic energy. Find the work required to lift a 1,000 kilo satellite to a circular orbit 29,409 kilometers. According to Newton, if you have two objects of mass They exert a gravitational force on each other of magnitude G times mass of the first object times mass of the second object divided by the square of the distance between them. Every single object with mass exerts a gravitational pull on every other object with mass. So I'm going to use only because I've had him before, so he's the one who gets to be picked on. You have mass, right?
Yeah.
Congratulations, everyone's attracted to you. Everyone in this room is attracted to you. Unfortunately for you, so are all the desks.
Yeah.
And the computer. And the camera.
Probably the calculator and everything.
Yeah. Everything that has mass is attracted to you.
Yeah.
So why aren't we all going flying towards him?
Cool. Negligible.
Why is it negligible? It's negligible with respect to what?
The distance.
I'm still not orbiting him.
What's G?
G is the universal gravitational constant. It's a universal constant. Last time I checked, your mass is nowhere near that of the Earth.
Oh, yeah.
Earth's gravity supersedes yours.
Because the gravity is also this, but on a much larger scale.
One of the funniest scenes.
Maybe you're in denial about this fat thing.
Oh, yeah? Well, I challenge you to prove to me that I'm fat.
Okay, hang on. See this?
Yeah.
You know what it is?
Sure. It's an apple.
Good. All right, watch this.
What the heck? What is this? What is this, some kind of gag?
No, that's orbit.
Huh?
You have your own gravitational pull.
Oh, that's a bunch of crap.
Now back to the Three Stooges.
Oh.
That's obviously an exaggeration, but if you ignore the idea that there's the Earth, yes, that would happen. Now, it's important to note that R is the distance between the center of mass of the two objects. We study center of mass Wednesday. But the center of mass for the Earth is the center of the Earth.
Just a quick question. Was there a reason that the objects were floating around him rather than sticking to him?
Yeah, that's how orbit works.
Okay.
So that's essentially how gravity works. It reaches a point where, right, so we orbit the sun, right? Why aren't we falling into the sun? Because of the way that the gravity works, right? It's not like you drop something, right? It's going to hit the surface, right?
Yeah.
But remember, the surface is not the center. At some point, if it could just tunnel, it would reach an orbit where it would start to fall with style, they call it. That's what orbit is. You're falling with style.
Oh, okay. But I guess it's not like a magnet or anything.
No, magnet would just pull you in. Right, again, that's also because gravity is more radial. The best way to describe it is, think of a trampoline. Put a bowling ball in the center. What happens?
Probably just go through it.
No, I'm not saying drop it. You set it.
It'll probably just pull it down.
It deforms, right?
Yeah.
Now throw a marble. Just kind of drop a marble. What's going to happen? It's going to go around the curve, right?
Yeah.
That's orbit. That's how gravity works. Gravity is the distortion of the fabric of space-time.
Okay.
Has to be a very large distortion to actually fall into the center. So again, that's why I said that was an over-exaggeration of how gravity works.
For now, I'm going to ignore what G actually equals. I'll come back to it. Our function would be G times, capital M is always meaning mass of the larger object. Mass of the Earth. So this symbol, by the way, is the astronomical symbol for the Earth. That's the astronomical symbol for the Sun. Every planet has its own astronomical symbol. Times the mass of the smaller object, satellite, 1,000 kilograms, all over little r squared. So work $1,000 I was writing fraction. Times G times mass of the Earth, because they're all constant, times the integral of just 1 over r squared, dr. What is the lower limit for integration?
Is it 0? Oh, no, it is.
That?
Uh-huh.
What would be the upper limit?
That number 229,409.
How'd you get those?
Well, It's going to a circular orbit says, it seems like that number would be the radius, like the distance between where it's floating around and the object itself, which would essentially make that the radius.
So why 0?
Because at 0, it's actually at the object that it would be orbiting around.
What's the object? So what's the larger object?
The Earth.
What did I say little r measured?
29,409.
For F, what does little r represent?
Is that like the distance between once it's at orbit, the object and the
It is a distance.
yeah.
Distance between the center of masses. For a satellite, we can just treat it as a point mass. So is that 29,409 distance from the center of the Earth? This is the distance we want.
So it's 29.
So what would this distance be? You don't have to give me an actual value.
It'll just be X or something. It'll be the distance from the top of the Earth to like the core.
What's that called?
The radius?
Radius.
Yeah.
That's the radius of the Earth.
Okay.
So the lower limit is not 0, because that would be you assume it starts at the surface, which does. But the surface has a distance from the center. The radius of the Earth.
Which would make the upper limit 29,409.
Now, I'm simplifying this problem, because I'm ignoring elevation. Right? I'm assuming that the launch is at sea level, which is I think how they measure the radius of the Earth. I'm assuming that the surface of the Earth is completely flat. So it's not like there's a mountain on there that actually now increases the elevation. Right? Because if we were launching from a specific height off the surface, then we wouldn't be starting at the radius of the Earth. It would be radius of the Earth plus whatever the elevation is. So oversimplifying this. And then yes, this would then be that plus the radius of the Earth. Let's call that. Oh, wait a minute. Sorry. That's not entirely correct. What's force measured in? What's the SI unit for force?
Is it what? Inch pound?
Units?
What's the SI unit for force? It's named after the guy who defined it.
Newton?
It's the Newton. But the Newton is actually not a unit, it's a combined unit. It's the kilogram meter per second squared. The kilogram meter per second, to be more precise. Right, because it's mass, which is kilograms, times acceleration, which is meter per second per second. We don't have SI units. The kilometer is not SI, but the kilogram is. I need to write that as SI, which is the meter. So it's times 10 to the 3. Now I'm going to make a simplification because I don't feel like writing that out all the time. So I'm going to go R1 is going to be that distance. Just so I don't have to keep writing that out. I'm going to start signing as R1. So what is that antiderivative?
It would be negative 1 over r.
So what this is going to equal, negative 1000 g mass of the Earth times 1 over R1 minus 1 over radius of the Earth. Notice this value in here is going to be negative. Right? R1 is larger than the radius of the Earth, right?
Oh,
Which means this is smaller than this. So this is going to be a positive value.
Right.
Because you have negative times negative. And by the way, that is how I would leave it in physics. Newton's gravitational constant. And again, I say, this is actually incorrect. Newton was wrong. This is not how gravity works. That's how gravity works for smaller objects. When you start to do really, really large objects, then you have to use general relativity. And gravity becomes a lot more complicated. There's the gravitational constant. 6.672 approximately times 10 to the minus 11. That is a really small number. Because gravity is a very weak force. You overcome it every single day. In fact, I'm overcoming it right now just simply by lifting.
Because if you weren't overcoming it, you would be pressed to the floor.
Oh, look at that. I just overcame gravity again. Gravity is very weak. In fact, it's the weakest of the four forces. Mass of the Earth.
is.
5.975 times 10 to the 24th kilograms. Yeah. Armin, you're not even magnitude 10 to the 3rd kilograms, I would imagine. Maybe magnitude of 10 squared. Yeah. That's 22 orders of magnitude larger than you. That's why we're not all flying towards you. The Earth doesn't even notice your existence.
Yeah. Don't think I'm as big as this.
Oh, by the way, the Sun is order of magnitude 10 to the 30th. So, yeah, the Sun doesn't even notice the Earth. The Earth could collide with the Sun, and the Sun might burp a little bit. That'll be about all that happens. And the Sun is actually relatively small. It's a normal star.
Compared to
A red giant. Betelgeuse is the closest known red giant. I actually don't know the magnitude of that mass, but it's much larger than the Sun. So I think a good comparison would be Earth to the Sun is kind of like Sun to Betelgeuse. Our Sun isn't even big enough to go supernova. It just kind of fizzles into a white dwarf. And then radius of the Earth, (6.37 times 10 to the 6th meters. If you plug in those values, what you wind up with is this work is about 5.14407 times 10 to the 10 joules. Now that is a lot of energy. That's 51 billion joules, give or take. So in the video, I do calculate escape velocity for the Earth. We've succeeded it. So escape velocity is just how fast you have to be able to actually overcome Earth's gravitational field and leave the influence of the Earth. I think it's something like 14,000 kilometers per hour. Something like that. We've achieved it multiple times. And the reason we call black holes black, the escape velocity of a black hole is faster than the speed of light.
You'd have to travel faster.
Yes, to be able to escape its gravitational pull. So, in other words, the black hole has so much gravity that not even light can escape its gravitational pull. Once you pass the event horizon, that's called the point of no return. As long as you're outside of it, you're fine. Thing's called the Schwarzschild radius. You're fine. Once you cross that threshold, you're not coming back.
There I am. I'll let you work on that one. And again, these slides are posted, so. Next set of math assignments will be due April 17th. Should be able to work on assignment 14. That's work. Did you have a group assignment that went up the Monday before spring break? That'll be due the 27th, which is Wednesday. Second reflection went up over spring break. That's just a real simple assignment. That is also due the 27th. And I am going to give you an opportunity to earn half the points you lost on the exam back by correcting the exam. You will do the corrections on loose leaf paper. You will attach it to the original exam and hand it back on April 1st. I need the original exam so I know how many points you lost and how many points to award you back. How I will grade it is I will just assume like it was the first time you took it, give you a point value. I will then take the difference between what you got originally and the new corrected value and divide it by 2. That's half the credit you lost. And then I'll give you a new grade. I'll add those points back into the original grade. So it should help everyone. I say should. For those who walked in late, the average was not good. The average was a 37. And I was taking out the one person who didn't show up for the exam. Yeah, they weren't good. Someone got a 1%. Actually, I think it's less than a 1%. It just rounded up to 1%. There was an 81 though. So that was good. I was originally grading and was really upset because it was like, I think an 81 wound up being like a 60 something, a high 50, low 60, but I forgot that the exam was at a 75 and not 100. So I'm going, holy shit, these exams suck. Oh wait, it's at a 75, okay, good. Not as bad as I originally thought. So that'll be due April 1st. Obviously that means that solutions to the exam are not posted yet. I will post the solutions on April 1st when you turn in the corrections. Make the most of it. Have a wonderful evening. See you Wednesday.